right, here we are. We're going to talk about an isentropic process today in this video. That's what we'll start with. Remember, constant entropy is going to give us an isentropic process. Now, if we have an ideal gas, and remember we have constant entropy, if we write our equation, we've got S2 minus S1. That's going to equal 0 because entropy is constant. That's got to equal the S degree at T2 minus S degree at T1 minus R times natural log of P2 over P1. Alright, so if that's the case, if this equals 0, because we're only dealing with isentropic processes here and we always have constant entropy, that's going to be 0. Let's go ahead and solve this equation for this term here. So we have S degree at T2 equals S degree at T1 plus R times the natural log of P2 over P1. Now, what we're going to do is I want to solve for P2. Okay, so if I want to solve for P2, we could essentially rewrite this expression and say P2 equals P1 times the exponential, so this is like e to the x, except we're not going to have an exponent of x. Our exponent is going to be S degree at T2 minus S degree at T1 over R. So essentially we just solved this equation for P2. That's what we did. Alright, and that's what we got. Now, keep in mind that's an exponential there. That's the exponent. Let's go ahead and rewrite this as P2 over P1. Notice here we've got these terms subtracted. So if we rewrite it as P2 over P1, then we're going to have the exponential of S degree at T2 divided by R over the exponential of S degree T1 divided by R. So now you got that. Okay. Now there are variable names for these things. We're going to say that this is equal to PR2 over PR1. Now the good thing is, because you might be wondering what am I supposed to do with this, these PR values are going to be found in the table. Alright, so PR is the exponential of S degree T, whatever your T is going to be, divided by R. And these are found in the ideal gas table, so A22. So isn't that convenient? So if we look at A22, here you go. So here is PR. Notice it says when change in entropy is 0. So that's telling you isentropic right here. So here is PR. So you would just come over here, look up your temperature, find that PR value. Notice there's also a VR here. So let's talk about that. Since we have an ideal gas, we can say that V is equal to RT over P, and VR then would just be RT over PR. Alright, so the same PR from above. And this is in table A22, or your ideal gas table. Alright. So those are some equations we're going to be using for the isentropic processes. Now, if we've got an ideal gas with constant specific heats, and we're still talking about an isentropic process, which means constant entropy, then we have a few more equations to write down. So you could go through and develop a equation that relates the temperature changes to the pressures. So if we have T2 over T1, that's going to be equal to P2 over P1. The exponent here is going to be K minus 1 over K. There's also one with temperature and specific volume. So we'll have T2 over T1. That's going to equal V1 over V2. Exponent there is K1. And then finally, we've got P2 over P1 equals V1 over V2 with an exponent of K. So these you might want to highlight there because we're going to use those. Anytime we have an ideal gas with an isentropic process and constant specific heat.